All right, we can go ahead and get started. So today for the UTIG discussion hour, we have Zach Sickmann here, who is a postdoc at UTIG, has been around for a few years, and he's going to tell us a bit about the sand crisis and what that looks like in Texas.
Cool. Okay, yeah, I mean, so since this is kind of a small group, if anybody has any questions or anything, I just unmute yourself or put it in the chat and we can just talk. And then I guess anybody that wants to see it later can see the recording. So basically what I'm going to talk about today is some progress on this Blue Sky project that UTIG very generously funded. And this idea originated a couple of years ago. As I started working in these natural systems that had some sand mines in them, and I saw that the sand mines were kind of perturbing the natural system, started learning a little bit more about sand mining and kind of the environmental impacts and the kind of human system around sand and sand mining, and kind of came to this realization that, like, wait, I know a lot about sand. Maybe I can carry this into the human system, carry these observations into the human system. And so as I'll outline in a minute, one of the big questions in sand mining is demand is really high these days. And so anytime you have high demand, you have an incentive to produce the most economically cheap and easy supply to meet that demand. And so oftentimes that incentivizes illegal activity. And so in a lot of places in the world, there are these illegal sand supply networks where there are areas that have been deemed too environmentally sensitive, or sand mining has been outlawed, or export of sand has been outlawed for one reason or another, but demand is just so high that these illicit supply networks develop to exploit the resource anyway. And so one of the difficulties in managing that is that unless you're directly observing the extraction, the transport, and the final use, you're kind of out of luck regulation wise. And so what I thought I would try to do is use sand provenance analysis, use my expertise in looking at the composition of sand to tell where it came from, to see if we could develop methods to, quote unquote, fingerprint these illicit supply chains. And not to give the answer away on the title slide, but it's going to work. Okay, so recently I've been fortunate enough to be asked to be involved in a couple of working groups organized by the UN Environmental Program on kind of the future of sustainable sand mining policy. And one of the phrases that comes up in a lot of these meetings is sand is the new oil. And so, what exactly does that mean? Well, they're both natural resources, and they're both pretty foundational to modern infrastructure and modern society. But the way that I kind of like to conceptualize it is sand is quote unquote the new oil in kind of three different ways. So first, like I said, it's a foundational natural resource with few viable alternatives. And so one of the things that actually sets sand apart from oil is that, at least in terms of in the energy sector, at least we have developing alternatives, solar, wind, et cetera. There's at least some transition that's plausibly in sight. But with sand, there's not really a plausible transition on the horizon. And the reason for that is largely due to the fact that sand is a construction material. And so this image is just an iPhone photo of my driveway here in my house, just to illustrate the kind of fact that concrete is sand. So concrete is just about volumetrically the most pervasive building material in modern society, and it consists of cement, aggregate, and water. And that aggregate material, basically the volumetric matrix of the concrete, is sand and gravel. Sometimes it's crushed rock, but at least the finer component of it is virtually always natural sand. And you can kind of intuitively understand the reason for that is, like, how do you artificially generate a million individual particles of a wide range of sizes that will interlock, when they're cemented together like this and into this very durable medium? You can do it, but it's very kind of time and cost intensive. Or you can just let nature do it. You can just go out into the river and you can let mechanical and chemical processes generate these tiny little individual particles for you, and then you take them and you make this building material. So number one, sand is a foundational resource with few viable alternatives. Second, sand extraction can be directly and indirectly hazardous to natural environments. And so this is kind of an image taken from another project that I have on sand mining in the Ganges River in Bangladesh, basically illustrating the volume that we estimate is removed from the river annually. And so, these mines are basically removing one large sandbar worth of sand on an annual basis. And this is a problem, obviously, because not to mention the perturbation to the natural environment, the perturbation to the ecology, the fisheries, the vegetation. A lot of these places, a lot of these river environments are places that people live. And so when you take sand out of the river, you're taking away a crucial component of a natural system that needs to be able to dynamically evolve and respond to natural processes. So sand extraction is an environmental hazard. And then finally, sand is a source of conflict and inequity globally. So like I said, anytime you have really high demand for a material, there's an incentive to illicitly meet that demand. And so all over the world, particularly in the developing world, there are these criminal industries that are developed around overexploitation of sand from the easiest and most accessible sources. And usually that means rivers and beaches. Obviously, it's a lot easier to fill a dump truck full of sand on the bank of a river than it is to go dig a big hole in the ground and disaggregate lithified sandstone, so on and so forth. There are these criminal organizations that are organized around supplying for that demand. And then, of course, in terms of inequity, as is so often the case in natural resource exploitation, the most underserved communities are always the ones that are subject to the worst of the environmental consequences of this. And there are numerous examples globally of kind of an intentional blind eye being turned towards the environmental impacts of sand mining, such that urbanization, urban growth, and infrastructure expansion is done explicitly at the expense of vulnerable communities that live in these environments that are being exploited. Okay. So in terms of some kind of broad goals of improving the state of sand mining going forward, there's lots of work on finding alternatives to natural sand and gravel. This is an engineering problem that at least a couple of people here at UT are working on. Better defining supply and demand, basically better quantifying how much sand is being extracted from certain systems, how much natural sediment supplies in those systems, what are the environmental impacts that result from that balance or imbalance between the two. Better tracking of informal or illicit supply chains, what I'm trying to do with this project. And then, in terms of natural resource overexploitation globally, one of the big themes in terms of future policy directions is finding equitable and sustainable regulatory policies. And what the United Nations Environmental Program frames this as is the concept of just transitions, saying that, that we know that this resource needs to be extracted, and we need to figure out a way that it can be extracted kind of equitably going forward. We need the resource. It's going to have some environmental impacts. We can't tell people to just stop mining sand for a number of reasons, not the least of which is that a lot of these communities rely on sand mining for their jobs, for the primary employer of the region. And so focusing on this balance of just transitions going forward and focusing on regulatory policy that kind of balances the human and the natural needs of both sides of the system. Okay. So what does the sand trade look like? What are we trying to fingerprint here? And so I've highlighted a dozen or so countries in blue just to show where sand comes from in various parts of the world. And one of the biggest areas of concern is here in Southeast Asia, where countries and municipalities like Hong Kong and Singapore are growing very rapidly, but they have very little access to their own domestic natural resources. And they have to import sand from other countries. And so particularly here in Southeast Asia, countries like Malaysia, Vietnam, Thailand, Indonesia they all have some form of a ban on export of sand over concerns of overexploitation and the environmental impacts of the overexploitation of sand from rivers like the Mekong, the Irrawaddy, so on and so forth. So what we're trying to do is we're trying to provide a method that can be used in areas like this that doesn't rely on, satellite imagery tracking of where barges are coming from. It doesn't require like GPS trackers on every truck. Something that we can use the actual composition of the sand to say something about where it's coming from, to make import-export regulation a little bit easier. And so, like I said, what I'm going to do in this study is use my expertise in studying natural sediment dispersal using the composition of the sand. Basically illustrated here schematically. If we have some mountains and one's producing blue sand, one's producing red sand, one's producing yellow sand. The sand, the composition of the sand in these deposits that are being mined ultimately reflects the composition of the source regions, and we can use that information to say where sand is coming from and where it's ending up through the supply chains. Okay, so what does a sand mine look like? And we'll start here with this sand mine that's actually in Austin, or just southeast of Austin. So generally, the process of sand mining involves taking sand from some natural deposit. Here, this is Pleistocene Colorado River sand. Sometimes they have kind of a dredge vessel out here in this pond. Sometimes they just have excavator trucks that load the sand onto this conveyor belt right here. And then this conveyor belt carries it to a washer and a classifier. And this washer and classifier basically washes out all the clay, dumps it into one of these holding ponds, and then classifies the sand into fine aggregate and coarse aggregate, basically sand and gravel. And this is what that looks like. So sand comes in on this conveyor belt, it goes through some screens, it goes through some sieves, and then it goes through this washer right here that basically kind of hydrodynamically sorts the material into sand and gravel. And then some concrete plant or some trucking contractor sends a truck in, they go around the loop, they fill up with whatever they want, gravel, sand, they go out, the truck gets weighed, and they go off into whatever part of the market that they're taking the sand, usually to a concrete batch plant. And so this process of basically extracting the natural deposit, washing it, and size sorting it is basically the processing that goes on. The processing that goes on from kind of source to sink in this system. And so the questions that we wanted to answer for this project are, is there anything in the processing or washing of this sand from the natural deposit as it goes into the commercial supply chain that alters the natural compositional signatures? Is there sufficient regional leverage to define distribution networks in detail? Basically, is the sand coming from different mines in different places compositionally distinct enough to actually use that information to define the supply chain? And then finally, can we develop some cost-effective ways to determine sand provenance? Because obviously the answer is yes, we can do this, but it's impractical if it's going to cost $1,000, for every sample that you want to run. Okay, so to do that, I was originally going to do this like big whole North America thing where I was going to look at sand from the Pacific Northwest and Texas and the Appalachians, because I thought that I was going to have to go big to get enough compositional leverage. But it turns out, as I developed Texas as a case study, there's more than enough compositional leverage here in Texas alone. So what I did to start here was I just mapped the sand distribution network in Texas. And so I'll actually pull this up in Google Earth in just a second, and we can kind of fly around and look at what this actually looks like. But basically, I started with looking at where the natural sand deposits are in Texas: Quaternary sand, Neogene sand, Paleogene sand. This is basically Wilcox Group. And then these are like Woodbine Delta, like Cretaceous sand and gravels. Turns out these are not commercially exploited, really, at least for concrete sand. So they don't really need to be on this map. But the Quaternary and then the kind of older parts of the Neogene sand are. So every red dot here is a sand mine. And so basically I took a mineral resource map that the BEG made and updated it. The sand mines across Texas have expanded quite a bit since that map was published in the mid-2000s. So I just went in and looked at satellite imagery and basically updated all the new sand mines across the state, and I'll show you what that looks like in a second, in one particular area up here in Llano. And then concrete batch plants. So basically these are, you know, if you order a yard of concrete that comes in a concrete truck, you know, you're pouring a foundation for your new house or for a sidewalk or something like that. That concrete gets mixed in these batch plants that are in these white triangles. And then quickcrete, so bagged concrete. Like if you go to Home Depot and you buy a bag of concrete, one of the really popular brands around here is called Quickcrete. And then there are seven plants that make quickcrete in Texas. And so from this, we can basically define the source, the supply chain, and then kind of the final sink. And we can look at it both at a very local scale with sand that is coming out of these sand mines and going into a local batch plant. And we can look at it at a more regional scale with this bagged concrete that is being produced in these yellow diamond quickcrete plants, and then is being shipped to a much wider distribution network across whatever region the plant is in. And I'll show you what that looks like now. Okay, so let's see if I can just switch to Google Earth real quick. All right, you'll see Google Earth.
Yep.
Okay, cool. Okay, so here's Austin, and here are the sand mines that build Austin. This is the Colorado River. We can zoom in. We can zoom in down here. This is that sand mine that I was shown in those slides. So basically, all of the sand that goes into the concrete, particularly the batch plant concrete in Austin, comes from these mines right here. And so I'll turn on my not color coordinated symbols, now yellow circles are sand mines, and we can zoom out. And you can see that basically like every major metropolitan area in Texas, your San Antonio has their own kind of sand resource that they use. Usually it's Pleistocene deposits from the major rivers in Texas. You know, so Houston gets some of their sand out of the lower Colorado and also the Trinity. Dallas also similarly has, you know, their own supply chain. El Paso has their own. West Texas kind of gets it out of the Pecos. And then South Texas gets it out of various mines that are located along the Rio Grande river system. Okay, so that's basically where the sand comes from in Texas. And then on kind of the local supply side, in terms of like the big building projects, it generally goes into one of these concrete plants, which are, yeah, these red circles. Okay, so these are located wherever demand dictates, and basically the shipping of this sand is pretty expensive. As you can imagine, you know, these trucks burn diesel. They have to pay a driver, insurance, all these kinds of things. They're very heavy. They burn a lot of resources. They burn a lot of energy resources. So generally speaking, concrete batch plants get the sand that goes into their concrete from the most proximal source. So that kind of defines the kind of local supply chain network. And then we turn on the quickcrete plants here. Yeah. And so the quickcrete plants also similarly get their sand that goes into their bagged concrete very locally, but then they distribute much more widely. So like the San Antonio quickcrete plant here in northern San Antonio supplies all of the valley down here in South Texas, and then it also actually supplies up here into Austin. This quickcrete plant here west of Houston kind of supplies the coastal plain down here towards Victoria up through the eastern part of Austin. So on and so forth. Dallas supplies the northern I-35 corridor in the Dallas area, Abilene, Central Texas, Amarillo, the Panhandle, so on and so forth. Okay, so to generate a sample set to try to use the composition of the sand to define this known supply chain, I'm going to turn off these. So first, I got some sand mines to very generously collaborate, and let me come out and sample here. So I've got 3 or 4 different sand mines in the Austin area. that let me come out and sample the raw sand in the pit, and then drive around and sample each individual one of these classified piles, basically concrete sand, gravel, and then they've got masonry sand, which is like a finer sand here. And then I've also got cooperation from a mine down here in San Antonio, which is great. So that's kind of the sample set that's going to show how much this washing and classifying changes the natural compositional signature of the sand. So that's very good. And then I got some cooperation from a company called Tex-Mix that runs a bunch of batch plants in Central Texas. And so they let me come out and sample the sand pits in all of their batch plants. Zoom in this one. Oh, that one is not constructed yet in the satellite image. Zoom into the New Braunfels one. This one's pretty big. All right. So basically the way that these concrete batch plants work is they've got a big pile of sand, a big pile of gravel, and then they've got their cement, their lime and their fly ash and some other stabilizing things that they put into this mixer right here. And then these concrete trucks back up into this mixer. They get the mixed concrete and they go out to whatever job they're going to go pour the slab on. And so Tex-Mix let me come in and sample the sand piles at 7 or 8 of their batch plants around Central Texas. And then I talked to the plant manager and asked what mine did the sand come from. And so, we can carry the compositional signature of that sand all the way from the mine that I sampled through the batch plant, and just kind of show how that signature is preserved from quote unquote source to sink here. Okay, so that's kind of defining like how the actual process of the mining and washing and processing might affect the natural signature of the sand. And then to look at using these compositional signatures to define broader distribution networks. I went around, I'm going to turn these mines off. I went around to a bunch of hardware stores across the state and bought bags of concrete and washed the cement out, just poured it into a 5-gallon bucket and kind of washed it with a hose until all the cement was gone. And then I'll show you what that looks like in a second, until just the sand was left. So doing that, you can basically define the boundaries between the distribution networks of the different Quikrete plants. So what I did is I sampled this area in Central Texas pretty heavily to find the distribution network boundary between the West Houston plant and the San Antonio plant. I don't know exactly where it is yet, but anecdotally, it seems to kind of run down I-35, where this sand up here, this Quikrete up here in Austin is actually coming from San Antonio. It's not coming from West Houston. And I'll show you how easy it is to see just with your eyeballs, the difference there. And then I happened to be going up to Colorado a couple of weeks ago. And so I sampled the kind of central panhandle corridor to find the boundary between the Amarillo distribution network and the Abilene distribution network. And I'll show you what that looks like in terms of the sand composition in just a second. And then Llano here is a really interesting little like microcosm of a case study. So this concrete plant right here, it's run by the Lauren Concrete Company. So this plant right here supplies concrete to kind of this part of the hill country, up into Mason and kind of this area here. But what's really interesting is that the Llano plant actually gets its sand from this sand mine right here, which is right in town, and takes sand directly out of the Llano River. And interestingly, this mine didn't exist 10 years ago. So this mine has just cropped up to meet demand. Everybody wants to build a nice ranch house in the hill country these days. We're in 2015. There it is. It pops up sometime between 2015 and early 2017. But basically, this story of like increased demand is not just a developing world story. It's also a Texas story, as anybody that's lived here over the last 5 years can attest. People are moving to Texas, and that demand is being met by increased natural resource extraction. Now, it doesn't really matter that the sand is being taken out of the Llano River here because it can't get to the coast anyway, because there's like half a dozen dams on the Colorado River system that would prevent that in the first place. But it's kind of an interesting little microcosm of the story here. And then interestingly, this is a tractor supply. This is a tractor supply company right here, and they get their quickcrete from the West Houston plant. So that's a cool little local versus regional distribution network story. Okay, that's kind of all I have to show in Google Earth right now, I think. Does anybody have any questions about Texas supply chains while we've got the map pulled up here, or sand mining or anything? Okay. So let's go back. Let's go back into PowerPoint. Bugger, which talk is it? That one, right? Yeah. Okay. So let's go from current slide. Okay. So I was surprised how well this is going to work in Texas. Like I said, originally I thought that I was going to have to sample a much broader swath of North America, a much broader swath of the country, to find sand mines and sand distribution networks that were producing sand that was compositionally distinct enough to actually provide a useful case study. But it turns out that Texas has more than enough leverage here. So what these jars have are the sand and gravel that was washed out of the bagged concrete, the quickcrete that was purchased across Texas. And so this jar here on the left is showing what the bagged concrete that is produced in the San Antonio plant looks like. It's a very quartzose sand. And this image doesn't show it very well, but the coarse aggregate, the gravel component, is crushed limestone. Makes sense for anybody that's familiar with South Central Texas geology. There's not a big river like the Colorado River running through that part of Texas that's producing this really nice arcosic sand. So to get the gravel component, they use crushed limestone. And then again, this very quartzose, very distinct sand in the fine aggregate. There's a question mark here because I'm not 100% sure this is coming out of the Dallas plant, but I'm pretty sure it is. But it's a much more kind of mixed mineralogy sand in this very lithic rich gravel. The Abilene plant produces a really pretty like pink sand that's very distinct, very easy to distinguish from the other areas with just the naked eye. Amarillo here produces a slightly different sand composition, but a pretty similar gravel composition. And then I don't have a picture of the jar from the West Houston plant, but I'll show a zoomed in photo of what it looks like. But it's just Colorado River sand. Like it's just like Llano uplift, lots of potassium feldspar, quartz, basically pretty typical Colorado River mineralogy. And then just here for like just major contrast, here's some aggregate from some bagged concrete that came from the Bay Area. And so along with Matt Malkowski, I've got another sand mining project in the Bay Area. And we were out there a couple of months ago to sample around there, and we got some sand from some sand mines out there. And while I was out there, I figured that I would just buy a bag of quickcrete and rinse it out and see what it looks like. And it looks just like the sand that's coming from the mines that we're studying, and also very compositionally distinct from anything in Texas. Okay. So the plan from here. So I've got the sample set, and I'm in the middle of processing it. And so what we're going to do, like I said, is we're going to start from kind of mine through processing to see how this washing and sorting affects the compositional signature of the sand. We're gonna run the gambit. We're gonna do petrography, bulk geochemistry, heavy minerals, and detrital zircon. I'm gonna throw everything at this initial look just to see how anything changes. Some of those definitely might change in terms of the hydrodynamic sorting. of different mineral assemblages of different densities. But that'll be a nice baseline. But like I said, things like detrital zircon analysis, heavy mineral analysis, like these are not practical solutions in a regulatory sense, because not very many places will have the funds or access to an LAICPMS to actually like get a detrital zircon signature from some barge full of suspect sand. So in terms of actually developing this into something that can be used in a regulatory capacity, we have to think about the most simple and cost-effective way to use the composition of the sand to say something about where it came from. The solution that we came up with, or that we're in the process of refining, is an image analysis-based system. So what I was thinking as I was processing these samples is that with my eyes, I can tell very distinctly immediately, like as soon as I wash the first bit of cement out of a sample, I know which plant it came from. And granted, like I'm something of an expert in sedimentary provenance analysis. I've got a trained eye, so fine. But if I can see it with my eyeballs, we can teach a computer to do it. I think, and initial results suggest that we can. Okay, so here are 3 photos of sand that was washed out of bagged concrete. So this came from a Home Depot out here in Northwest Austin, but it actually originated from the San Antonio Quikrete plant. This is a sample that came from Llano that we believe actually originated from the West Houston plant and the Colorado River sand source. You can see a lot of this pink stuff is chunks of granite and potassium feldspar. Consistent with derivation from the Llano uplift. And this is from a bag of concrete that I bought at a Home Depot up in Temple. And so this one we think is coming out of the Dallas plant. And I should say, with respect to defining the supply chain for this bagged concrete, I've had a lot of phone conversations with the different plants at Quikrete. And they basically say like, yeah, well, it depends where the trucks are going. They like, oh, we can define this like general distribution pattern, but there's not really like a set distribution pattern. So to the best that I've been able to independently verify where this bagged concrete is coming from, directly from the plants themselves, I've got a pretty good idea there. And then we'll just have to look at what the actual samples show. But suffice it to say that like there's a Quikrete plant in Abilene. I bought a sample of Quikrete in Abilene. Like it came from the Abilene plant. And so I bought a bag of Quikrete from every city in which a plant is, and then we use that in the most immediately proximal samples to kind of define what the signature of that plant looks like, and then we can use that to kind of broaden out and define the boundaries between the different distribution networks. Okay, so let's look at what this sand actually looks like. So this is a zoom in of the San Antonio sample. We can see that it's mostly quartz, some chunks of broken up limestone, pretty consistent color wise. This is from something that's coming out of the West Houston plant. We can see these broken up pieces of granite, these potassium feldspar grains, lots of quartz. There's also some some sedimentary lithic fragments that are preserved in here as well. But you can see that even between these 2 samples, there's a color difference. And then here's the sand that's coming out of the Dallas plant up north. And again, some of these more polished lithic grains, still lots of quartz, but there's enough color leverage in between these samples that we're going to try to teach a computer to distinguish between them. And initial efforts suggest that it's going to work. So basically what we did is we photographed a couple of these end members and basically took an RGB value from every pixel within some defined square of the sample, and then we plotted it up and used principal component analysis to determine what the best discriminating metrics were to kind of define the signatures of the end members here. And so it works pretty well. Of the seven samples that we did this for, They are all distinguishable based on just this RGB pixel map alone, except for 6 and 7 here, which have 100% overlap. But it turns out that 6 and 7 have a massive grain size difference. And so the next step that we're going to work on is we're going to add size sorting and rounding to this image analysis scheme. And so that, like, the actual code, like the actual method for doing that exists. We just need to kind of figure out how to plug it into our initial, like, very simple RGB pixel map. And so the reason that this works here is that this sand is very clean, it's washed. All the clay and organic matter and stuff has been washed out of it. And it's generally speaking fresh river sand. So, you know, this method wouldn't really work for like a weathered sandstone, or it wouldn't really work for kind of a grungy, chemically altered or diagenetically altered set of sand. But the sand that goes into concrete is very clean, very fresh river sand that is washed. And so the actual spectrum of colors that is produced by the individual grains in these samples is more representative and more consistently representative of the mineralogy of the source regions, or at least that's kind of our working hypothesis here. And again, the initial efforts here suggest that it's going to work, or at least it's going to work in Texas. So if we're thinking about something that is actually going to have a regulatory impact, something that, you know, a border patrol agent in Malaysia can actually use, you know, they can take a picture with their iPhone, plug it into an app, say, what part of the world are you in? You know, what sand sources are you concerned about? Does this image analysis scheme that incorporates information on the color, the size, the sorting, the rounding of the sand, is that consistent with the sand being derived from the source that it is proclaimed to have been derived? Yes or no? And then that's a pretty simple initial discrimination metric. And then you know, samples that have some cause for concern can then be interrogated in more detail. But it seems like this image analysis scheme is gonna provide at least a useful initial discrimination tool and kind of a tiered system of suspicion, so to speak. And then the really I think powerful thing about using the composition of sand to track supply chains is that the information lasts forever. So this is a picture of the skyline in Singapore, and all of the concrete in these buildings is made with largely natural sand, and the composition of that sand, once it's set in cement, doesn't really change. You know, so this question doesn't have to be kind of a caught in the act question. The cityscape, you know, the built environment, the concrete built environment, can basically be treated like a sedimentary basin in a certain sense. The compositional information that is in the sand is kind of held in perpetuity. So if ever there's a question of some building project, to the sourcing of the material, the sustainability of that source, so on and so forth, the information is there. And so here's kind of an interesting illustration of that. This again is that picture of my driveway here in North Austin. And this is a picture of the slab and the patio of the house I used to live in during grad school out in California. And you can see that, you know, pretty easily distinguishable. This sand did not come from Texas. This sand did not come from California. So that same very simple image analysis scheme, if we build a big enough training data set, and we are clever enough, hopefully it can also be used to discriminate sand sourcing, you know, in just kind of polished slabs or kind of rough slabs of concrete, not just the individual loose sand samples. And then, of course, for this training data set that we're going to generate for the image analysis, we're also going to do bulk geochemistry and petrography in all those samples. So we'll be able to say, yes, we can discriminate based on these image analysis metrics, and then we can provide the underlying reasoning, the underlying mineralogy, that the mineralogical explanation for why that's the case as well. And then conceivably going forward, if you were to develop a similar data set in an area of concern, you would have a pretty simple check on if sand is coming from an illegal source or not. Okay, that's it. That's the state of the project as we speak. So I'm happy to have a discussion on anything about this or sand mining generally, or any questions that y'all might have.
Hey, Zach, it's Matt. Nice job. Quick question about the illicit component of this. Is it more the volumes of sand being extracted? In other words, some places are taking too much, or is it more about specifically where it's coming from?
It's a bit of both. So like I said, Malaysia, Vietnam, Thailand, Indonesia all have complete or partial bans on exports. So if you're in a country that is not Malaysia, Indonesia, Vietnam, or Thailand, and there's a building project that is purportedly getting their sand from some legal source, and in fact it is coming from Malaysia, so on and so forth, then that's a problem. And the issue is that the enforcing an export ban on something like this is virtually impossible, because these sand barges just exit the Mekong Delta at night and then they chug across, whatever body of water to wherever they're going. And for all intents and purposes, there's no way to track that unless you can actually see through satellite imagery or GPS tracking, where that barge is coming from. So in that sense, that's a pretty easy question, insofar as this country has banned exports of sand. Did this sand come from that country? All right, that's illegally derived sand. Now, this is not like a silver bullet that solves all problems, because as you say, if there is a source of sand that is a legal source of sand, but it's being overexploited, that doesn't necessarily tell you if this sand was extracted at permitted levels, or you know what I mean. So it's kind of a application specific method, but there are actually quite a few places in the world where sand mining is completely banned. Like lots of tributaries in the major rivers in China, sand mining is completely banned for environmental reasons. So in those areas where there's a complete ban, if you see any sand that is compositionally consistent with derivation from that banned source, then there you go. Yeah, Jamie.
So are there, and I apologize if you said this, but are there so thinking of Texas, are there Texas state regulations or even city regulations on how much sand that they can take? And then are they do they have geologists that work for them and to figure out replenishment of the sand? And is somebody checking that they're not just taking all the sand from the Colorado River? Like, I'm curious how regulated this is in the state.
Yeah. So the short answer is I don't know what governmental body regulates sand mining in Texas. I actually know a lot more about regulation in California than I do in Texas. But one thing I do know is that the mines on the Colorado River, they have to be offset from the active system. So you see, like all these mines here, they're mining in the inside of this meander bend. Okay. So they're mining Pleistocene deposits. So they're not allowed to dredge directly from the active Colorado River. However, up in Llano, they are doing that. But like I said, the sand in the Llano River doesn't have a snowball's chance to make it to the coast anyway. So that's not really the problem.
But so they're essentially mining private land, like they
yes, yeah. They buy a ranch, or they lease a ranch or whatever, and then they dig up a bunch of sand from it, and then they generally do a pretty good job of reclaiming the pit, revegetating it to the extent that they can. Yeah, but I mean, one of the really interesting issues in sand mining is that there's not an alternative. You want to build a house, you want to have a slab foundation on that house, you have to mine sand to build that house, right? And so Texas, I think in general, the river mines do a pretty good job of not perturbing the system, or at least not perturbing the system worse than the dams are already doing. But I can look into who actually regulates sand mining in Texas. I don't know.
No, it's fine. I think I had a misconception that some of this is public land. So
No, not these pit mines, no.
Okay.
Well, okay, but in Llano, yeah, actually. I mean, in Llano, this is a city park, right? So like the mine actually does it. Matt Malkowski and I actually kayaked up here and sampled the river right here the other day. But yeah, so like technically this is public. They are mining public sandbars and stuff here.
Zach, another general question. Do you happen to know if in thinking about mass balance of these systems and perturbing them, whether or not any of these companies have looked into the viability of going into dams, right? So the dams are naturally sequestering the sediment, and that becomes problematic because then the dams fill up. I mean, is it just is there a grain size problem in the dams, and they would have to then sort it all out? What's the deal there?
So the only information I have on that is anecdotal. A conversation that I have with a plant manager. But at least in Austin, they're not allowed to, for a couple of different reasons. But there are some other environmental concerns about running motorized boat, basically like motorized dredging vessels and stuff in the dams around here. But that the plant manager that I was having this conversation with made a similar point to what you're saying here, is that like this sand is building up against the dams and it needs to be dredged out. Why not dredge it out and use it? Why not dredge it out and use it in the same way that they're using this pit mine sand for? But at least in Austin, there are regulations around motorized boats and other environmental things that currently prevent them from doing that here in Austin. But like in New Orleans, they do that. Like they dredge various channels in the Mississippi River. And a lot of that sand is used either for land reclamation or for other commercial purposes.
I had a question about how your image analysis with the app might work. So how do you see that? Like if it does work and everything goes great and you can figure out where your sand is from, how wide would your database need to be? Like, would you have to sample kind of as many places as you did in Texas all over the world? Or do you think you could go broader?
Well, it depends. It depends on how similar or distinct the sand from different sources is. And so, like I said, when I was initially trying to develop this case study, I didn't think that there was going to be enough leverage in Texas. And the more that I sampled, the more that I realized there was plenty of leverage. So in Texas, the sand in these different systems is distinct enough that just like two or three representative source samples seems like it's enough to define distinct families that you can use to discriminate. But that having been said, I have never seen a handful of sand from the Ganges, the Brahmaputra, the Irrawaddy, the Mekong. So I don't actually know. Taking this, the lessons that I've learned here in Texas and how surprisingly well it worked, I would say that maybe you don't need as many as you think you need. But obviously the larger the trainings, and so, we have big ambitions here with machine learning and fancy algorithms and stuff, and so obviously the bigger the training data set, the better, in terms of if you're going to use something in a regulatory capacity, like you want to be darn sure that you're right. So the bigger the data set, the better, but it entirely depends on how compositionally distinct the sand is.
Yeah, especially because, Texas has like these different rivers. It'd be interesting to see like if sand mines like along the Mississippi or something, how different they are compared to like different states or something.
Yeah, totally. And so another really interesting thing about Central Texas is that the Llano feeds into the Colorado, right? And so it seems, based on our initial look at the sand, that the Llano is distinct from the Colorado, because the Colorado integrates sand, all the way back up into West Texas and New Mexico. And then the Llano is basically just draining the Llano uplift here in Central Texas. So it's got a lot of granite in it, which is where a lot of that case bar is coming from. And obviously the Llano is a very important sand source for the Colorado River because that granite disaggregates really nicely into sand. But the Llano is not picking up all of this other more far traveled stuff. So it seems like we can distinguish not only the major trunk streams, but we can distinguish the more unique tributaries to the trunk streams, which is nice.
Cool. Any more questions for Zach?
Cool.
All right.
Well, thanks, y'all.
Thanks, Zach. Nice job.
Thank you.